Well, we're back with a certain kind of probability distribution today. It's called a binomial probability distribution. Well, there's four things that have to be true for it to be a binomial distribution. I will tell you that I'm more concerned with you learning how to navigate the formula, which you see here. But this must be true. The problems that I give you, these conditions will be met. One, there's got to be a fixed number of trials. That means, like, if I'm tossing a coin, how many times are you tossing it? Like, it's got to be set. Each trial has to be independent. That means what I get for my second, like, head coin toss has nothing to do with what I got on my first coin toss. So each one is independent of the last one. Binary outcomes. Binary means there's success or failure. Yes or no. There's only two possible outcomes here. Either you did it, or you get it, or you don't. So success or failure is usually how it's put. And the last one is the probability for each success is the same. That means if I'm flipping a coin 10 times, right, that's a fixed number of trials. Every time I flip it, it doesn't matter what the last result was. There are only two possibilities, heads or tails. And each time I flip it, there's a 50% chance it's heads. So that all these conditions are met. Now, all the problems I give you, those conditions will be met. So your concern is learning this formula. All right, now look at it. The probability of x, and we'll kind of break out these variables in a minute, is, see, we've seen this before, NCX. Remember, on your calculator, at least if you have a 84 or 83, you're going to find this in math, and then there will be a probability, like when you press math, it has some options and probabilities on the end here. And if you scooch over to there, you'll see NCR. So we're going to use our calculators for this. So N is the number of trials, and we're going to do some examples, but in your notes you want to jot this down, so when we're doing an example you can glance down. N is the number of trials. Notice it appears here and here. X is the specific number of desired successes. P is the probability of success, whatever we define that to be. Basically, success is getting what you're asking for. Like if I want to know about heads, I would classify heads as being a success and tails as being a failure, right? So success means getting what I want. Failure means I don't get that. It's binary, yes or no. And so Q is the probability of failure. So we need the formula, and we need to know what the variables are. So this is going to launch us into our first example. What I'm going to do is I'm going to rewrite this formula up in the corner so you can see it while we're working through a problem. And we're just going to run through it. You're going to see it's really not bad once you learn how to use the formula. These are kind of easy to compute. A lot less going on than our last lesson we had. So let me get rid of some of this. We're going to recopy this formula. NCX, P to the X, Q to the N minus X. All right, example 1. Suppose that I've done a lot of research and I found out that the probability that someone's favorite color is blue is 0.312 or 31.2%. So then I could ask a question. What is the probability P of X that if I ask 50 people if their favorite color is blue, exactly 10 of them say yes. Now what I've done here is I've created a situation where the answer is a yes or no result, right? So I'm not asking people what is your favorite color. There could be multiple answers there and it would not be binary, so it wouldn't be binomial. Your question has to be phrased so it's yes or no. So see, I'm just asking them yes or no. And I'm asking about a probability of a specific number. Like, I'm not saying what's the probability of a person saying it's blue. I'm saying what's the probability that exactly 10 of those people that I asked would say blue. What is that probability? So it's very specific. So that's the scenario. And what we have to do is we have to lock down these variables. I really wish I had a little more board space for this. So I have to erase the setup in order to make some board space. So it's important in your mind you understand what's going on here. All right, so I want to know, let's just tick them down here. N would be 50 people. I asked 50 people if their favorite color was blue. That's the total number that I'm asking. The number of trials is how we phrase it here. X is 10. X is the specific number I want to know about. Do 10 of those 50 people like blue, yes or no? So N is the total. X is the specific number I'm interested in. P is the probability of success. Now, success in this problem is they like blue. So what is the probability that a person likes blue? 0.312. Right, that was given in the question. Q is the probability that it's a probability of failure, that they don't like blue. Well, if 31% of the people say they do like blue, then 1 minus that will be the probability that they don't like blue. It's the complement. So this would be 0.688. So there's a 69% chance that they don't like blue. 31% chance they do, 69% chance they don't. Success, failure. See, the equation looks intimidating. All the descriptors I put are a little confusing, but it actually makes a lot of sense. Like, these problems, they're not too bad. Once you see what the variables are, you just got to pick them out. N is the total trials, in this case the total people. X is the specific number I want to know, the probability that exactly 10 of them, that's specific. P is the probability of success. Well, what is the question asking? Do you like blue? Success is yes, failure is no. There's a 31% chance I get a yes, and then 1 minus that is the chance of getting a no. Well, that's the setup. Here's the equation. Let's see how this plays out. So the probability, see that X, that 10 people like blue would be 50C10. That's how many people I asked. That's how many people I'm curious about. Like, I want 10 people to say they like blue. 50 people asked, 10 people like blue. The probability of success is 0.312. And see that X again? That's 10. And then the probability of failure is 0.688. And see this N minus X? That's just the rest of the people. That's the leftover people. So if there's 50 people and 10 of them like blue, that means 40 of them don't. 50 minus 10 is 40. So the way I would learn this is the total number here. This is the specific number that I'm interested in there. This is the specific, and this is the rest. So I want 10 of the 50 like blue, The rest of them, that would be 40, don't like blue. Once all the numbers are there, all I have to do is punch this in my calculator. So I already kind of did it, but if you go through, I'll just do it like and talk while I'm going through it. So I'm pressing 50, math, moving over to probability and picking NCR. Now I'm pressing 10. Now the way I do it is I'm going to press enter right now. I get a really big number. Then I press times, and I'm just going to put 0.312 to the 10th, and I'm going to press enter again. And then I'm going to press times 0.688 to the 40, and that will give me a probability of 0.029, or in other words, there's a 2.9% chance that if I ask 50 people if they like blue as their favorite color, 10 of them will say yes. 3% chance that 10 of them will say yes. Well, what if I asked it a little differently? Let's take the same case, but now let's say, what's the probability that 15 people said that blue is their favorite color? So instead of 10 people said blue is their favorite, what's the probability that out of 50, 15 of them, so more of them like blue? How does that change the problem? I still asked 50 people. Now I want to know the probability that 15 of them like blue the best instead of 10. And these are still the same. It's still 31% chance that they like blue the best and a 69% chance no. So how does that change my equation? Well, now I want to know the probability that 15 people like blue the best. And that's going to be the total number, 50, C, the number I'm interested in, 15 in this case, times the probability that they like blue, success, 0.312. And I want to know if 15 of them like it, and this is they don't like it, and if 15 like it, and I ask 50, then 35 of them don't like it. See, this would be 50 minus 15. It's the rest of them. So if I punch this in my calculator, I already calculated that, I get the probability of 15 is 0.120. So I've got a larger, there's a more of a chance that 15 of them will like blue than just 10 of them liking blue. I know, it's a little bit weird of the way I got to phrase the question, but the calculation isn't bad once you see how you pull the numbers out. So there will be a couple problems on the test like this, where I give you one scenario, and I give you a specific number, like 10 or 15 or whatever, and you have to punch the stuff in the equation. Another one on the test is kind of a single setup in which I can ask you multiple questions. So let's see how that goes. All right, I'm going to erase this equation now because I'm going to need the space. So in this case, let's say that I survey people on their favorite flavor of ice cream. And 28% of the people say vanilla is their favorite. 41% of the people say chocolate is their favorite. I gotta write smaller. Vanilla was 28%. Chocolate is 41%. Strawberry, 13% like that the best. And other is 18%. So something other than vanilla, chocolate, or strawberry. So this would be the setup. Now I can ask you questions. So I'm going to ask you 3 questions, all from this data. Question 1. What is the probability? Here, let's put it this way. I have to add another layer in. I walk into an ice cream parlor and there are 32 people eating ice cream. So I'd have to give you that information as well. So if I ask if I look around the room at all 32 people, they're all sitting there eating their ice cream. Question 1, what is the probability that exactly 11 people are eating chocolate ice cream? Right? So you get the scenario. I kind of, ahead of time, I knew some statistics, like 28% of people think vanilla is the best and so forth. And now I walk into a specific ice cream parlor, and there's 32 people sitting in there eating ice cream. And I just look around and see who's eating what. And I ask, what is the probability that if these numbers are accurate, which you will assume they are, that exactly 11 of the 32 people are eating chocolate ice cream? So how do we do that with the equation we've been using? Well, we obviously have to focus on this number right here. I really don't care about these values when I'm answering this particular question. So let's see. Let's identify the things. The total number of trials would be the total number of people is 32. The specific number I'm interested in this problem is 11. I want to know if 11 of them like chocolate. And since it's talking about chocolate, the probability they do like it, success, is 0.41. The probability they don't like it, failure, that would be 1 minus that, which works out to 0.59. So that's the data I need. Now I just need to punch it in the equation. So let's set it up. How do you find the probability that 11 people like chocolate? Well, it's the total, C, the specific number, times the probability of success. They do like chocolate. So 11, I want to know if 11 people like it. So how many people are left over that wouldn't like it? The rest of the 32, this must be 21, right? 11 people like the chocolate, 21 people don't like the chocolate. So I'm going to punch this in my calculator. Actually, I already did it, and I get 0.109. So there's a 10.9% chance that 11 people would be eating chocolate ice cream in this scenario. For number 2, I'm just going to change things up a little bit, and I want to show you, this is how it'll be on a test. I'm going to give you this data. I'm going to give you a setup like this, and then I'm going to ask you a bunch of questions without changing this data. So this would be question number 1, right? So for the test, imagine this is still there, and now I'm going to keep going down below. So here comes question number 2. What is the probability that exactly 4 people are eating strawberry ice cream? See, all I did was do a slight tweak here. I changed the number and the flavor. We're still going to use this data, except now, instead of looking at chocolate, I'm thinking about strawberry. So let's figure out our important numbers. I would strongly suggest you do this when you're taking the test. How many total? Still 32 people in the parlor. What's the specific number I'm wondering about? If 4 people like strawberry, what's the probability that they do like strawberry? 13. What's the probability that they don't like strawberry? 1 minus 0.13. There's the numbers. Here's the setup. The probability that 4 people like strawberry would be 32C4 times 0.13 that they like strawberry. How many people like it? 4. Times the probability that they don't like strawberry. How many people don't like strawberry? If 4 people do, The rest of them don't. So that'd be 28, 32 minus 4. And I just punch. See, once I get the numbers, you just punch it in your calculator. Definitely practice that before you take a test. Like, just once I get the numbers, make sure I get the right answer. And when I plugged this in, I got 0.208. So almost a 21% chance that 4 of those people out of 32 would be sitting there eating strawberry ice cream. So we'll do number 3. Oops, this was question number 2. My bad. Question number 3, you probably guessed we're just going to switch to vanilla, and I'll change that number. More of the same. So I hope you're feeling it like once you get the hang of it, it's very repetitive. So here we go. I'm just going to change this word to vanilla. Let's call it 10 people. And let's see how it changes the problem. I'm still using the same data, except now I am focused on the people eating vanilla. So, total people, still 32. This time, the number I'm wondering about, 10 people. What's the probability that they actually like the vanilla? 28%, 0.28. What's the probability that they don't like vanilla, failure? That would be 1 minus 0.28. That's 0.72. There's my information. Let's set up the equation. What's the probability 10 people are eating vanilla? Well, 32 total. 10 people like it. The probability they like it, and 10 people are eating it, times the probability they don't like it, and the rest of them, so 10 are eating it, 22 are not. Punch that in your calculator, and I got 0.139, so that'd be almost 14% of the people would be eating vanilla ice cream. All right, the problem should be in your notes that are posted. Practice these. They're very, like, once you get the hang of them, I think these should be easy points on your test. Just be sure you can do it. And be sure you're actually punching in your calculator, see if you're getting the right number. And like if I got an error or if you have a question, definitely please email me. You can't put comments on these videos because in order for kids, meaning people under 18-year-old, to be able to access this, I have to make it so you can't do comments. So you'll have to get your questions to me through email. All right, one more lesson before we're done with this unit. We'll hit that next. Have a good one.